Okay, so let's talk about algebraic functions. So this material is out of section 1.2, basically. It's not all of 1.2, but it's from there. 1.2 talks about several types of functions, and I'm going to do this one at a time, but one of the main types is algebraic functions. So here we go. Actually, I talk about other things first. So first of all, a polynomial, a function of this form where we have a number, so a naught, a sub 0 could be any real number, plus another number times x, plus another number times x squared, plus maybe another number times x cubed, all the way up to, say, x to the n, where n is n is greater than or equal to 0 and an integer. We're only doing integer powers of x. Like this is x to the 1, x to the 2, x to the n. I could put an x to the 0 here if I really wanted, right? Because x to the 0 is just 1, but I won't write that there. So if the function has a form like that, then we call it a polynomial. So actually, yeah, maybe as I go, I'll do this example down here. So since I just talked about polynomials, let me check off all the boxes that are polynomials. So for example, this one's a polynomial. And maybe it isn't written the way you expect. The way I wrote it up here is you put the lowest powers of x first and the largest power of x is at the end. But of course it doesn't have to be that way. You know, you can rearrange the order of addition if you want. The point is, all I see is integer powers of x. I see a number times an integer power of x plus another number times an integer power of x. I should emphasize these are positive integers. You don't see x to the negative 3 or x to the negative 2. And so, yes, this is a polynomial. This one is not, for polynomial, you're not allowed to divide by anything. There can't be any division. Well, you can't divide by, you could divide by a constant. So I could divide by 2, but I can't divide by something with an x in it. This one is also not a polynomial. Polynomials don't involve roots like this. So I see roots all over the place. Also, polynomials don't, there's a lot of reasons why this isn't a polynomial. There's a trig function, and that can't be involved in any polynomial. There's an exponential part, and that's also not in a polynomial. There's also a logarithmic part. Any one of these things would be an automatic no. Okay, so those are that's what polynomials are. A function that can be written as a polynomial divided by another polynomial is called a rational function. So it's a rational function. It's like a fraction where a polynomial is on the top and a polynomial is on the bottom. So then let's go through these and talk about whether each one is rational. Well, this one isn't a fraction, but you know what I can do? I can always just draw a line here and put a 1 on the bottom, and that's the same thing, right? And if I did that, the 1 on the bottom would be a polynomial. 1 is like 1x to the 0, and that's a non-negative integer power of x. For example, that's like when this number is 1, and then the rest of the stuff just isn't there, like you just stop. So the function that's just plain 1 is indeed a polynomial, and I can rewrite it that way. I can write it over 1, and so I would say, yes, this is a rational function. Even though it may not look obvious at first glance, you can put it over 1, and then it's a rational function. In fact, any polynomial is automatically a rational function because you can always do that. You can always just put it divided by 1. Anyway, let's do the next one. This one looks like what we were expecting. This is obviously a polynomial on the top and a polynomial on the bottom. So that's a yes. This one is no. It is a fraction, but the top isn't a polynomial. The top is involving roots, and polynomials don't have roots. They only have non-negative powers of x, like x to the 0, x to the 1. Roots are like fractional powers of x, like this is like x to the 1/2, and you don't see that in polynomials. And this one is just no. I could try to put this divided by 1 to make it a fraction, but that wouldn't really help because the top would not be a polynomial. The top is involving all kinds of things that can't be involved in polynomials. So that's a no. Okay, let's move on. So now I get to actually defining algebraic functions, which is kind of the name of the lecture here. An algebraic function includes both polynomials and rational functions. It's more general thing. It's any function that you can form from powers and roots of x. You're allowed to add them to each other, subtract them from each other, you're allowed to multiply them together, you're allowed to divide them, and you're allowed to do composition. Composition is like plugging a function into another function. So, I'll show you an example in just a second. But composition is like when you're doing f of g of x. That's composition. Any such thing is called an algebraic function. And an algebraic function automatically includes all polynomials, because polynomials, how do I make a polynomial? I just take some powers of x, some integer powers of x, and those are all included among the algebraic functions. And then I add them together. I multiply them by coefficients, and then I add them together. And those are operations that I'm allowed to do to algebraic functions to make more algebraic functions. So polynomials are all automatically algebraic. Algebraic functions also allowed me to divide. So if polynomials are algebraic and I'm allowed to divide, then rational functions are also algebraic, because a rational is just a polynomial over another polynomial. So if the top is algebraic and the bottom's algebraic, then the whole thing's algebraic. So that makes some of this easy. Polynomials, rational functions, automatically algebraic. This one wasn't a polynomial, but it was rational, so it's automatically algebraic. This one, well, we don't have an automatic answer here. This doesn't mean the answer is no. This means we have to look at it. And actually, looking at this again, the only reason why this wasn't a rational function is because of the roots. But algebraic functions are allowed to have roots. And this is so this is also illustrating what I meant by composition. So if I break this apart, like the first thing I see is this, I'm sort of covering this up with my fingers. The first thing I see is the square root of x. That's algebraic, because algebraic functions include roots. Then I see that I'm adding x squared, and that's also algebraic, because algebraic functions include powers of x. And then I'm allowed to take the cube root of that, because the cube root is an algebraic function, and I'm allowed to do that function of another algebraic function. I'm allowed to compose the cube root function with the algebraic function that you see underneath. If I wanted to, I could, so you see this plus 3 here on the outside. If I wanted to, I could put a 7th root over the whole thing, stuff like that. And it would still be algebraic. So that's what I mean by composition here. You're allowed to do algebraic functions of other algebraic functions. And of course, the bottom is, I see just powers of x, so that's algebraic. So that one's a yes, even though these were no. Now the last thing is still going to be a no. Even though algebraic functions sounded quite inclusive, It's really just powers and roots and anything that you can build up from it using these basic operations. And that doesn't include anything trigonometric, anything exponential, or anything logarithmic. So again, any one of these three things, as soon as I see it, I know the answer is no. All right. So then let's talk about functions that are just integer powers of x. So like when f of x is just x to the n, where n is a positive even number, let's say. So the first one I'll talk about is n equals 2, and that's a very familiar graph. That's your standard parabola. It basically looks like this. I'm not the world's best artist, and these are hand-drawn, of course. But we all know what this picture looks like, basically. And I just notice I've specified a couple of points. So this is the point -1, 1. This is 0, 0. And this is 1, 1. For larger even powers, here's what happens to the graph. They all kind of look very vaguely the same. And I'm going to go into the differences, but let's focus first on the similarities. They go down and then up. And they all go through the same 3 points, -1, 1, 0, 0, and 1, 1. They all go through all 3 of those points. And they all go down, and then they hit the very bottom at this point, and then they go up forever. So that's the similarities. What are the differences? Roughly speaking, the difference is when you look at larger even powers of n, the graph just becomes sharper. You're going, for the down part, because as I go from left to right, I go down until I hit here, and then I go up. And for larger values of n, for the down part, I'm going more steeply down. And then when I reach the area down here, there's this sharp turn between when I'm going down and when I'm moving more to the right. And then, you know, these are all they're symmetric around the y-axis. So like there's the right side is a mirror image of the left side for all of these. And so what you see on the right side is just the mirror image of the left side. So it looks sort of flatter here for the larger powers of n, and then it goes sharply upward. So this is my drawing of n equals 4. And then just to show you like what happens kind of in the end, if you look at really large powers of n, like n equals 100, what you're going to see is it almost looks like it's just going straight down. And then there's almost like a sharp corner here, and then it's going straight to the right, and then it goes straight up. It's not really a corner. If you zoom in on the graph, you'll see that it's like a smooth curve. It's not like a sharp corner, but unless you zoom in, it's a bit difficult to see that. It looks kind of sharp. So that's what even powers of x look like. By the way, the domain is all real numbers. The range is all non-negative numbers, so 0 to infinity, including 0. And these functions are not one-to-one, of course. To test whether they're one-to-one, you do the horizontal line test, and these all fail the horizontal line test, of course. All right, what about odd powers? So let's talk about x to the n when n is an odd positive integer. Of course, the first value is just n equals 1, and y equals x to the 1. I mean, this is just y equals x. This is just a straight line with a slope of 1. So that's a very familiar graph. And then here I have, so for n equals 3, we're talking about y equals x cubed, And that's also kind of a familiar graph. You should have all seen that before. And then for larger values of n, what you see is kind of analogous to what we talked about before. Here I chose a pretty large odd value of n, 101. And what it looks like is kind of just a sharper, exaggerated version of this graph. This graph, roughly speaking, it's always on its way up. As I move from left to right, I'm always going up, up, up. But it does get a bit flat around here. So it's going up steeply, and then around here it's going up a lot less steeply, and then it starts going up steeply again. And that effect is just exaggerated the larger n gets. And for a very, very large value of n, once again, it looks like it's basically going straight up, and then there's a corner, and then it moves straight to the right, and then it moves straight up again. And again, if you zoom in far enough on the graph, it's not really a corner, but if you don't zoom in, it kind of looks like one. The domain of these functions is all real numbers. The range is also all real numbers, and these are one-to-one. These do pass the horizontal line test. Even, and yeah, take my word for this, even around here, if I draw this horizontal line, even though I said for large values of n, this looks like it's almost flat in here, the horizontal line really does only cross once still, because it's not perfectly flat. The graph is never perfectly flat. For no value of n is the graph actually perfectly flat. It kind of looks like it until you zoom in far enough. And that's why this passes the horizontal line test. Okay. What about roots? So, of course, when I draw this and I write an n here, that's the same as x to the 1 over n. Roots are the same as fractional powers of x. And once again, I'm going to split it into even roots and odd roots. So let's talk about even roots. So this is the nth root of x, where n is a positive even integer. Of course, the first one is just n equals 2, in which case we're talking about the square root of x. And that's a pretty familiar looking graph. In fact, it's really just, if I take this graph, this is just when we were talking about the graph of x squared, for an even power of x. It's like I take this graph, I turn it sideways, and I cover this part up with my hand. Now that looks like the graph of the square root of x. In fact, that is the graph of the square root of x. That's this graph. They are the same thing, right? And for larger even values of n, you have kind of the same effect. It just becomes sharper. In fact, maybe I can even illustrate, like, going back to when we were, yeah, sorry to do it sideways, but I have to do it sideways because that's how it is. When we were talking about even powers of x, here we did n equals 4. Now, if I want to do the graph of the fourth root of x, what do? I take this, I turn it sideways, and cover this part with my hand. That's the graph of the fourth root of x. And that's what's here. That's what's here. So, right, and again, yeah, maybe I should stop switching back and forth from page to page, but this one is really just a sharper version of this one. And if you look at larger values of n, it almost looks like it's going straight up and then straight to the right, like a sharp corner. The domain is 0 to infinity, including 0. The range is the same thing. And these are one-to-one because these pass the horizontal line test. Even though, for example, this one looks like it's almost flat, a horizontal line still only crosses once. It's not literally moving straight to the right. It is going a little bit up as it goes to the right. Yeah, so for odd roots, let's talk about the cube root. I chose not to draw a graph of the 1th root of x. The 1th root of x is a bit silly. The 1th root of x is just the same as x, and we know what that looks like. So let's not talk about the 1th root of x. The smallest odd root let's talk about is n equals 3, the cube root, the 3rd root. And that's a fairly familiar graph. In fact, the graph almost looks like, say, the square root of x, but it's like I took another one of these looking things and put it down in the lower left, right? Because what's going on in the top right corner looks a lot like this. They aren't the same thing. Actually, this one is sharper than this one, but they look almost the same. It's just that this one has a thing down here. And yeah, so, I'm sounding like a broken record already, but for larger values of n, it's a similar picture, but just sharper. I keep using the word sharper, so hopefully you understand what I mean by that. The domain of these is all real numbers. For some reason, I put it in interval notation, but you can also write this. These mean the same thing. The range is also all real numbers, and these are 1-to-1. They do pass the horizontal line test. Okay. So let's talk about absolute values. So most people regard absolute values as extremely easy, but then it's common to get tricked by absolute values in some ways. So let's talk about it. I would say there's 2 valid formulas. Well, there's probably more than 2, but I'll talk about 2. Here's one. The absolute value of x is just x if x is greater than or equal to 0. And that's an answer that we were expecting. We all know that if x is greater than or equal to 0, the absolute value doesn't do anything. The absolute value of x is just x. But then the second part sometimes confuses people. The absolute value of x is negative x if x is less than 0. So there's also this other valid formula, but before I talk about that, let me just show you an example using this first formula that I showed you. And let's do the absolute value of 3 and the absolute value of negative 3. Now, please bear with me, and we all know the answer. We all know both of these answers. What I'm going to do is I'm going to use this formula and demonstrate that we do get the answer that we expect. Absolute value of 3, I look here, I see, well, 3 falls into the first category. 3 is greater than or equal to 0. So the formula that I use is just x. So x is 3, and this tells me that absolute value of 3 should just be x, which is 3. And that's the answer we were expecting, of course. What about absolute value of negative 3? Well, negative 3 falls into the second category. So the absolute value of x, if x is negative 3, this is telling me I should do negative x. Okay, well, maybe this seems weird, but let me just write down what it's telling me to write down. So x is negative 3. I did negative x, so that would be negative 3, which is 3, which is what we were expecting. That's what this does. The reason why this confuses people is because they're forgetting that x is a negative number. So if you're writing down x, it has a negative sign on it already. and this negative sign cancels that negative sign, as we just saw, and makes it positive, which is what the absolute value should do. So hopefully you all now believe this formula. Let's talk about the other formula. Absolute value of x equals the square root of x squared. This is another one that can sometimes confuse people because they say, well, the square root of x squared, that should just be x. It's just not always the same as absolute value of x. But no, the square, formally, if you automatically just take the square root of x squared and replace it with x, you're making a mistake. You might be right, but you have to think about something else first. You might also be wrong. If x is a positive number, then you're going to get the right answer, but if x is a negative number, then you won't. Anyway, let's once again do the absolute value of 3 and negative 3 using this formula. Square root of 3 squared, that's the square root of 9. And when you do the square root of 9, the square root of 9, if it's written just like that, it's just 3. It's not plus or minus 3. It's just 3. So we all know sometimes there's this thing where I do the square root of both sides of an equation and then there's a plus or minus introduced. But if you see a square root written just like this, meaning, for example, we're not solving an equation. I'm just simplifying something. And in such a case, you always just do the positive square root. You don't put plus or minus. So this is just 3, and of course, that's the answer we were expecting. So then let's do negative 3. The trick is, negative 3 squared is 9. So from here, it's clear that we're going to get the same answer, and this is exactly what we expect. And that's why this works. If it's a negative number, then squaring it gets rid of the negative, and then doing the square root returns back the positive version of the negative number that you started with. And that's what the absolute value should do. So either of these is a valid formula, and this seems easy, but it's going to come up again. Since we were talking about domains and ranges and whether things are one-to-one, let's go over that too. So if f of x is the absolute value of x, then it has domain all real numbers, it has range from 0 to infinity including 0, and it is not one-to-one. And actually, I don't have a lot of space here, but the graph of f of x looks basically like this. It's like a V. It's like a straight line with a slope of -1, and then it switches to a slope of 1, and it goes through 0, 0. So, right, of course it's not one-to-one because it fails the horizontal line test. Okay, I'm almost done with this video here, but let me just go over real quick how to solve equations involving absolute values. There's two situations. You can have absolute value of x equals a, and a is a negative number. So if that's the case, if a is a negative number and you have this equation, that has no solution. The absolute value of x cannot be a negative number. However, if you don't have a negative number, you have a number that's greater than or equal to 0, and you have the same equation. This is true if and only if, and this is important, it's a double-sided arrow here. So I'm giving you all solutions for x. X is the plus or minus a. And of course, that's how it works, because if x is a, then the absolute value of x is a, and if x is negative a, then the absolute value takes the negative away, and you still get a. So real quick, let's do an example. Find all solutions to this equation. So the first thing I would like to do is get rid of the absolute values. And I know that this is it's a bi-directional step. It's a double-sided arrow. So I can take off the absolute values and write plus or minus 7. And of course, when I write an equation like this is really two equations. It's one of the equations is where this equals 7, and the other equation is where this equals -7. But we have a way of dealing with two equations at once, and that way is just by using this plus or minus symbol. So I'm going to carry out the rest of this. What I'm going to do next is I'm going to add 3, and as we discussed in yesterday, adding a number to both sides is an if and only if step. It's a bi-directional step. So I'm going to add 3, and what do I get? I write it this way, 3 plus or minus 7. And again, this equation is really representing two equations. One of them is 2x equals 3 plus 7, and the other equation is 2x equals 3 minus 7. Now I'm going to get rid of the 2, and I get rid of the 2 by, well, I can divide by 2. That's the same as multiplying by a half. And since I'm not multiplying both sides by 0, this is another if and only if. So 3 plus or minus 7 over 2. And we made it if and only if the whole way through. It's all double-sided arrows. So we know, because we're supposed to find all solutions, we know that we found all of them because of that. And what are they? Well, one of them is 3 plus 7 over 2, which is 10 over 2, so 5. Or 3 minus 7 would be -4 over 2 is -2. All right.